Hello, everyone. I'm honored to share my work with you. I'm Zhenxing and come from China. The topic is F-Flow, a promising countermeasure against DDoS attacks based on split sketch and PCA. This is the directory. First of all, we will make an introduction. After that, I will present the overview of F-Flow. Then I will anatomize the design of F-Flow, and thus the evaluation of our system would be given. First part is the introduction of the flow. As cloud, first let's reintroduce why we propose this system. As cloud computing becomes ubiquitous on the internet, it opens the door to many serious attacks, particularly distributed denial of service (DDoS) attack, as one of the most serious threats to cloud security. DDoS attack affects cloud and data center service even worse than to regular internet service. Regarding cloud and data center as an inherent multi-tenant infrastructure, DDoS attack against a single customer is against all customers in the infrastructure. In recent years, DDoS attacks evolved both in the quantity and the destructive power of a single attack. The peak bandwidth of the largest DDoS attack in 2021 exceeds 3 Tbps. DDoS attacks in such scale can easily break down arbitrary online service and incur huge financial losses. Cloud providers need to do more to ensure the availability of their cloud services. Attention thereby due to countermeasures against DDoS attacks. Towards online services such as cloud computing, our goals are DDoS attack detection and, more importantly, victim identification of network-wide DDoS attacks, so that outcomes can contribute to quick reaction to such devastating attacks. A promising DDoS countermeasure system must have the following for low properties. Low profile, the system should have the capability of detecting low profile network randomly so that DDoS attacks can be detected as early as possible. Low dimensional, in order to identify victim IPs of DDoS attacks, dimensional reduction mechanism is necessary for processing high dimensional data, such as per IP flow statistics. Low overhead, expensive computational cost and memory consumption should be avoided in the system, and low transmission. If the system is distributed, collaborative nodes transmit as little data as possible, not exacerbating network congestion caused by an ongoing DDoS attack. We will discuss later to show how our system achieves requirements. Therefore, we name it for low. One of the challenges is how to apply PCA on fine-grained per IP flows to help to distinguish victim IPs. Taking advantage of PCA, this method can figure out malicious OD flows that includes OD flows means original destination flows that includes low profile attack traffic. However, this method cannot result in particular victim IPs due to coarse-grained aggregation. Applying PCA on fine-grained per IP flows may help to distinguish victim IPs, but the data dimensionality jumps sharply to a high degree that PCA cannot afford to. To tackle this problem, Li et al. Use Sketch to randomly aggregate IP flows, although this method keeps input data of PCA in low-dimensional space is therewith poses another high overhead problem, that is to infer key IPs reversely from a number of particular buckets. This process always involves great space in memory for storing mapping tables, as well as high computational cost for calculate intersections of multiple large sets. Another challenge is how to reduce the data sharing among collaborative nodes. Original network measurements such as OD flows, statistics, and sketches are transmitted over the network to a centralized device, challenging sparing bandwidth capability of DDoS compromised leaks. Next is the overview of our system. Flow is a distributed framework for DDoS detection and victim identification. It consists of global detectors, GD, and local detectors, LD. LDs are widely deployed all over the network. For simplicity, we consider a classic distributed architecture as shown in the picture. In the flow system, GDs communicate with each other and LDs using reliable channels. In general, LDs detect traffic anomaly based on measurements of local traffic, while the GD confirms whether reported anomalies arise from network-wide DDoS attacks and infer victim IPs or partial victim IPs based on local detection results. Particularly, an LD performs a piece of a sketch that is a hash table of a special designed bitwise hash function. In this way, the LD aggregates packets into bitwise flows according to certain bits in their destination IPs. The aggregation significantly reduces the scale of time series measurements data of network traffic. LDs can detect when network anomalies occur and identify flows that involve these anomalies using a PCA-based anomaly detection method. After that, LDs send very little data to the GD, including IDs of anomalous flows. Then the GD integrates flow IDs into splits sketch and determines anomalies parading all over the network as DDoS attacks. There are three principles behind the flow system, making it scalable and practical in network-wide DDoS detection and identification. Principle one, flow aggregation based on bitwise information. Aggregating packets according to certain bits in their destination IPs. On one hand, reduces data dimensionality to yield PCA-based method. On the other hand, since flow ID refers part of victim IP, it benefits determination of victim IP. Principle two, combination of distributed traffic monitoring and minimum data transmission. Considering the nature of DDoS attacks, flow leverages pieces of a sketch on different LDs to gather network-wide measurements. Meanwhile, without sending original measurements, flow greatly reduces the amount of transmitted data between nodes, respecting limited link bandwidth. Principle 3, lightweight reconstruction of victim IP based on popularity. As a profit from bitwise hash functions, flow provides a lightweight way to infer victim IPs of DDoS attacks, having no use of storing mapping tables and calculating intersection of large sets of IPs like reverse sketch. Determining bits in victim IPs relies on the popularity of the bit in verified as 0 or 1 in accordance with the multi-source feature of DDoS attacks. Our flow system achieves desirable for low properties through our essential components: bitwise-based flow aggregation, split sketch structure, PCA-based local detection method, and novel IP reconstruction algorithm. First is the bitwise-based flow aggregation. In flow, LDs aggregate packets into flows according to certain bits in their destination IPs rather than whole destination IPs, thus obtaining much fewer flows. The principle of bitwise-based flow aggregation is specifying k bits positions in an L-length IP address. Packets whose destination IPs have identical bits in the same positions are assigned to the same flow. Let us define a function IP mask, where IP is an IP address and a mask indicates which k bits are specified. Mask is filled as an L-length bit string in which specified bits are set to 1 while others are set to 0. FIP mask combines selected bits in IP orderly and results in a k-length string. To identify flows, F is filled as flow ID. This figure illustrates an example of bitwise-based flow aggregation. IP1 to IP4 are different destination IPs of packets. Specifying 5 bits positions in an IP address, packets destined for IP1 to IP4 thus are divided into 3 flows. Given a fixed k, there are at most 2 to the power of k bitwise flows. LDs thus can achieve an affordable space overhead by varying k. Considering functionality of bitwise-based flow aggregation, we then regard F as a particular hash function called bitwise hash function. Accordingly, mask is the seed. In this section, we present the deployment of split sketch for network-wide traffic measurement. The split sketch is a virtual sketch structure that is divided into pieces and deployed on multiple LDs in flow. In split sketch, bitwise hash functions are adopted instead of regular universal hash functions. Imagine a sketch that consists of hash tables of n bitwise hash functions. Each hash table is a piece of the sketch puzzle, and each LD only performs one piece. An LD generates its own bitwise hash function independently by randomly choosing k integers from 0 to L subject 1. These integers correspond to selected bit positions in an IP address. Then the LD allocates memory space to keep a hash table of size 2 to the power of k. Since our flow system uses traffic volumes as a feature to detect DDoS attacks, each bucket in the hash table is a counter for counting the number of packets that are mapped into the buckets. When a packet arrives, the LD updates the bucket with index F by adding 1. Split sketch, it does not actually gather traffic measurements. Although the network into a centralized device, in fact, each row of a split sketch represents statistic of different traces. At LDs, we adopt PCA-based local detection method to detect potential DDoS attacks and identify abnormal traffic aggregates. The LD obtains a time series measurement of local traffic forming an N multiplying M matrix D, where N is the number of time intervals and M is the size of hash table. Let's Y represents a law of D, which is viewed as traffic fingerprint at a particular time to find residual important AFs. We eliminate the change caused by previous found AFs. Let omega be the set of previous found AFs. Each flow in omega corresponds to a four tuple Sn Fi Yi asterisk supplied dot I applied, where Sn represents the order of flow Fi being found for an anomalous Y is Yi asterisk plus delta I. Y asterisk represents the sample vector of four normal traffic conditions, and delta I represents the amount of change due to flow Fi. Then Y asterisk applied and delta I applied are best estimates of Fi asterisk and delta I, which are calculated in the procedure to find Fi. Then we can construct a new traffic fingerprint Y asterisk, getting rid of effects of AFs that have been verified to be anomalous. Y asterisk is Y subtract sigma delta I applied in terms of Y asterisk, the next AF can be found. The procedure is repeated until the change caused by any residual flow does not exceed a threshold. In view of traffic increase that accompanies nearly all flooding-based DDoS attacks, we improve above local detection method in two greedy ways. Further compress D to DS correct, SD correct, and measure the amount of packets that arrive in each time interval and perform anomaly detection upon Y, only if the increasing scale of packets amount in the corresponding interval exceeds certain threshold. When the global detection device finally determines the DDoS attack, it should consider the time when the abnormality occurs. If many abnormal traffic alarms occur in a short time, this can be considered that a large-scale DDoS attack has occurred in the network. As shown in the figure, a DDoS attack can be confirmed when LD0, LD1, and LD2 all report local anomaly alerts nearly in the same time. The determination process of abnormal burst period starts from the two abnormal alarms with the closest time interval. The initial observation window is set as tau, and then select the observation window to cover the above two abnormal alarms. Stretch the observation window along the two directions of the time axis, then the first abnormal burst period of the local detection equipment can be obtained. Based on the abnormal burst period of each local detection device, the global detection device finally determines DDoS attack in the network. A concentrated abnormal burst period of multiple local detection devices in a short time means a large-scale DDoS attack. By comparing the abnormal outbreak period of each local detection equipment, if the number of equipment whose abnormal burst period overlap in time is greater than a threshold N, then global detection confirms a DDoS attack is in the network. In order to confirm ongoing DDoS attacks and figure out victim IPs, GDs reconstruct anomalous destination IPs based on detection results obtained from LDs, benefiting from bitwise hash function used in split sketch. Our IP reconstruction algorithm has very low memory requirements and computational cost. Through local detection, LDs obtain a number of AFs, which are sent to the GD in the form of timestamp, flow ID, mask. Flow ID is the ID of AF. Timestamp represents the time when the anomaly occurs. Mask implies the particular bitwise-based hash function adopted by an LD. Combining flow ID and mask, we can extract an L-length vector in which bits specified by mask are set to 0 or 1. According to flow ID, we call the vector disparate segments of IP, DSIP. Regarding IP reconstruction as a vote for bits in victim IPs, then DSIP is the ballot. The GD first creates an empty vector B of length L to imitate an IP address, and then deduces the IP bits by bits on the basis of amounts of DSIPs, which set the bits to 0 or 1. To reduce the uncertainty in resultant victim IPs, we compare all DSIPs we compare all DSIPs with B and ref by unknown and amphibious bits as many as possible. If most refined bits in a DSIP match with B, we believe the DSIP is truly part of a victim IP. Other refined bits are unmatched only because no enough LD selects these bits in their hash functions. We thus can adjust statuses in B according to unmatched bits in the DSIP, reducing unknown bits. For amphibious bits, such multiply matched DSIPs help to decompose B into 2 or more vectors. Each vector corresponds to a distinct victim IP. This is the example of DSIP. The number of flow ID would be used to determine the specific number of DSIP with the help of the mask. In this section, we evaluate performance of flow system through simulation and theoretical analysis. We first measure an importance metric, coverage rates of selected bits by LDs in an IP address, which is relevant to performance of IP reconstruction. We define coverage rates as the proportion of bits in an IP address that are selected by LDs at least once. Each LD chooses k bits in an IP address to generate its own bitwise hash function. Then, for a bit, it is not selected by any LDs with the probability Q is 1 subject k divide L. The power is n. Accordingly, the theoretical expected coverage rate is 1 subtracting Q. As we can see in figures, the numerical and experimental coverage rates perfectly match with each other. When K is 10, L is 32, and N is 10. The coverage rate is more than 97%. Uncovered bits in an IP address are no more than 1. Namely, only 10 LDs participating in the flow system can cover almost whole IP address, thus potentiating precise IP reconstruction. We qualitatively compare our flow system with three existing approaches with respect to system overhead: sketch subspace SS, two-level sketch TS, and the reverse sketch RS, which are closely related to our approach. The figure shows the experimental statistical results. FLOW performs better than other methods in all aspects. The victim identification FN of FLOW system is slightly higher than that of RS method because only the number of complete IP addresses is calculated when the experimental data are counted. Since our approach may result in partial victim IPs, it is difficult to evaluate its accuracy in DDoS detection and victim identification. We thus incarnate the performance in an indirect but persuasive way. That is to evaluate the efficacy of outcomes of our FLOW system in filtering traffic towards victims. We also show the simulation results in the figure. In our simulation, most of partial victim IPs only have one indeterminate bits. Using them as rules, we can still successfully filter attack packets of DDoS attacks with false positive rates of less than 3%. All traffic toward victims is captured as their IPs matches with partial IPs. Finally, we qualitatively compare our FLOW system with sketch, subspace, two-level sketch, and reverse sketch. The goal is to demonstrate the advantages of our approach in computational complexity, space requirements, and communication overhead. When comparing computational complexity, we consider two aspects: the cost to update corresponding structures, which can be approximately reflected through the number of calculating hash value per packet, NHVP, the cost to identify victim IPs after detecting anomalies, COIV. In FLOW, each collaborative node maintains only one hash table of size n. One of the major differences between our approach with the other three is the way to map packets in a sketch. Our approach uses special design bitwise-based hash rate, while others use random hash in sketch, which induces completely different methods to identify victims. Most COIV of our approach arises from counting DSIPs and comparing every DSIP with the vector B. So the cost increases when the number n DSIP of received DSIPs proportionally. We summarize the comparison results in table in which n flow represents the number of distinct flows that SS needs to store states, and n BIP represents the number of anomalous destination IPs. Considering the number of DDoS attacks or victim IPs, the number NDSIP is much smaller than M and N flow. In this context, our flow system outperforms SS in all three aspects. Relatively, TS has the lowest cost O1 during victim identification and the expense of space. Even though approach TS and RS are slightly better than FLOW in some aspects, they all require much more memory to store statistics of network traffic. That is. Thanks for listening.